Hi, the lecture today is going to be a review of a variety of topics we have learned from the beginning of the semester related to the notion of limits. We are going to take a look again at the concept of tangents, velocities, and general rates of change. So we are going to go have a quick look at slope of the secant line and the formula for finding slope of the tangent line. I'll give some examples of that. Then we go ahead and look at the basic application, which is finding average velocity and instantaneous velocity. And then in general we are going to talk about rate of change of any quantity. So here are five basic topics for today. Let's start by slope of secant line. So item number 1 is slope of secant line. What is meant by this? The idea is that we have a function given to us we want to figure out the speed at which it rises. We go ahead and first concentrate on a base point, for example this point. We want to know how fast the function rises at that point. Our first attempt is at approximating it by figuring out some other point on the line, on the curve, connecting these two with a straight line and finding the slope of that straight line instead of the curve itself. This line by itself is called the secant line. So secant line refers to this. Now if your function is given to you by some formula y is equal to f of x, and your base point here is given to you as, say, point A. If you want to find the slope of this line, you need to find the ratio of rise to run. So to find the rise to run, I have to find out how far I have moved horizontally and how far I have moved vertically. I need to know these two and divide them to get my slope. So I have a run and I have a rise. I need to figure out the slope of the secant line, which is going to be the ratio of rise to run. Well, we have to refer to the second point in some fashion so that we can find these quantities. One way to do this is just to call the second point by whatever variable name you wish. You might as well just use this x. If I call this point x, so long as x is different from a, I'll be fine. And the run is going to be the distance from here to here, which is just x minus a. How about the rise? How can I find the rise? Remember, rise refers to this quantity from here to here. Well, an easy way to do that is to go back to what the definition of function is. It's f of x. The height at a, this height here, let's color it so that we see what we are talking about. This height from here to here is just f of a. That's what we mean by the function notation. F of a is how tall this thing is. F of x is the height of the function here. So if I go if I go on the y-axis, the height at this point is f of x. Rise is the distance from f of a to f of x, so the rise for me is going to be f of x minus f of a. That's the rise. So this ratio becomes f of x minus f of a over x minus a. Remember, a was a base of operation, x was some other point at which we have selected a point on the graph of a function, drew this line, call it the secant line. The slope of it is just ratio of rise to run. All we need to know is how to use this function notation to carry out these steps. Well, the next step we came to the issue of finding the slope of the tangent line. And to do that, we said, okay, let's take the same shape. Let's hope this is the same shape. And here's my point A. What I need to do is to bring the second variable point, called it x, bring it close to the first point. And that situation, the secant line turns into a tangent line, so we are going to have a tangent line so this is our tangent line. It has been obtained by moving that point close to the first one and observing what happens to this line itself. To carry that process, we need limits, so we had the slope of the tangent line. In this case, it was the limit of that expression. So we took the limit of f of x minus f of a over x minus a, and let x come close to a. So what we get here is the slope of tangent line. Now, two notations are used or two formulas are used in calculating tangents. One of them is just this one. The other one, it's customary to have a single letter attached to run. So in that case, they consider the second point, instead of calling it x, they might call it like a plus h. This notion of writing it as a plus h is like using a as a base of operation and then specifying explicitly how far to the right or left you want to move. So instead of expecting you to calculate the run as x minus a, the run might be given to you as h. So sometimes they use that notation and just call this h. In that case, this formula here is going to become, instead of x, I have a plus h, f of a plus h, and while the other ones stay as it was, denominator x minus a is going to be a plus h minus a, that's just h. So once again, second notation we have here for the run is just to call it, say, h. If we use that notation, then we will be allowed to use the similar notation here. Here I say limit of, instead of x, I write a plus h. A is as before. X minus a was converted to h. All that is left to decide is that what should I write here underneath. No longer have an x here. So what's happening? Who is the variable? Variable is our run. We are making our run smaller. What does h tend to? When that point comes close to this point, what does h tend to? Well, h of course tends to 0. So this is a second notation that we have here. There is still a third notation that many people use, and that instead of using calling it h, sometimes people call it the delta x. Okay, so sometimes instead of using that, people use delta x, and for the rise they call it delta y. So that's the third notation. While we are here, we might as well mention that as well. Let's write it with a different color. So here's a third way of referring to this. Sometimes people write delta y over delta x. So delta implies difference. So this means difference in y's, and that means difference in x's. So these are all same concepts. And if you wish to insist on writing a formula like that here, it would be limit of delta y. Hopefully you understand what that means, divided by delta x. Well, in this case, our delta x is going to 0. So three ways of talking about the same thing. You have to be comfortable about switching back and forth between these kind of notations. We probably use this one more often than the others, but they are all about the same. So let's go ahead and quickly solve a few examples. So here I'm going to have some examples. Let's start the very first one, a very simple problem. We have seen this before. F of x is equal to x squared. Next example I want to look at a bit more involved in algebra would be, say, 1 over x. A bit more involved perhaps is f of x using this, f of x is equal to radical x, say. Maybe I leave one of these things to you to do. F of x is equal to 1 over radical x. You see quite a few exercises like this in this section, and the objective is you do them quickly, precisely, and understand what the answer is. Typically you want to do any one of these problems under 5 minutes or less, and be prepared for the next chapter. So let's take the very first example here. We have so example 1, f of x is equal to x squared. Well, what do we want to find in any of these cases? In all of them we want to find let me specify find slope of tangent line at x is equal to a. Sometimes they give a specific number for you to work with. Sometimes you have to work with a parameter or a letter or a variable. Let's go with that. We have had several exercises with numbers themselves, so let's just work it out at a general point A. So what is it that I want to calculate? I want to calculate slope of tangent line, which we said is f of no, I'm going to use this notation now, f of x minus f of a over x minus a. How is the limit taken? It's taken when x comes close to a. What is this quantity? We name it what it is. It's a slope of tangent line. Slope of tangent line is this. Well, let's go ahead. We make a chain of equalities. Just write every step what is being done. X minus a, same. F of x, well, that f of x is x squared. F of a is a squared. X coming close to a. We go ahead and learn the tricks we have learned so far. Limit of, what can we do here? Simple exercise. We know this can be factored easily. It's just x minus a times x plus a over x minus a as x approaches a. Well, this quantity and that are the same. That's the quantity that makes numerator and denominator zeros. That cancellation is the essential step. We go ahead. We have equals to, continue, we don't break this chain of qualities, x plus a, x still approaches a. Now when x comes very close to a, x plus a comes very close to 2a. So what we have learned is that the slope of the tangent line to the graph of f of x equal to x squared at the point x equal to a is 2a. Let's make sure we digest that, understand what is it that we are talking about. But this is a simple function, it's just a parabola. So it was quick. We have this function. Here's our parabola. We have picked some point, call it a. So suppose this is my a. Question we are posing is that what is the slope of the tangent line here? Slope, we show the slope by letter M. Slope, the letter M is used for it. Presumably in French, the word for slope starts with M. At any rate, we found out that that slope is twice the coordinate that you start down here. What does that mean? For example, if this a was 1.5, what would the slope be? If I start at the point 1.5 on the graph of y equal to x squared, the 1.5 slope is 3. At 5, if when x is 5, slope is 10, and so on. So by doing the calculation at the point x equal to a, we with one stone actually, in fact, we are killing lots of birds. We're finding the slope everywhere on the function. It's just twice your starting point. Let's go ahead and do example 2. What was my example 2? Example 2 was 1 over x, a bit more algebra here. So I start with example 2. You have f of x was equal to 1 over x. Yes, it was 1 over x, excuse me. Yes, 1 over x. Slope, again, m is equal to limit of, use a stronger color, limit of f of x minus f of a over x minus a when x approaches a. So again, issue was finding the slope, find slope of tangent line at a. So limit of f of x is 1 over x, f of a is 1 over a, is x minus a here, x approaches a. Now we are getting into a bit more algebra, and that's what your background in algebra 1 and 2 come in. You have to be comfortable about simplifying these kind of expressions. You write limit word first, so we hope we have enough room here. Here's my fraction, the denominator of it xa, numerator of it. Maybe you want to pause, do this problem, come back, double check your answer. Are you doing that? Okay, we cross multiply, this is a, cross multiply these, this is x, and this is x minus a. Next, let's go down here. I have limit of, if I have a fraction divided by a number, let me just quickly remind you, if you have, use a different color, if you have, say, a over b divided by c, what is that? It's a divided by bc, is that right? So let's go back to here. I have a minus x, and then its denominator was xa, Now when I want to multiply with this, a parenthesis is essential. You cannot drop this parenthesis. It has to be there. Next, I haven't managed to do any cancellation. Do you see the cancellation? Again, pause, think about the cancellation and come back. Hope that you did that. Next step, one thing to pay attention to, this expression here, this one, a minus x and x minus a are just off by a minus. That is another thing, standard thing to remember. A minus b over b minus a is just minus 1. One of them is off from the other one by minus. So when you simplify, when I simplify these two, I am left with a minus 1. So next step here, I have limit of minus 1 over ax as x approaches a. Well, when x approaches a, this x is a, you'll have a times a, that's a squared. Your answer will be minus 1 over a squared. That is the slope of the tangent line. Again, let's go ahead, make sure we understand what is it we are talking about here. Let me draw this function quickly. Maybe you want to go ahead and draw it first and then come back and look at the drawing that you have, compare it against mine, make sure you could do the problem on your own. Okay, our function is y is equal to 1 over x. You make a table for this with your calculator, or so let me go ahead and quickly draw this. Do you know that what's the name of it? It's called what? It's called a hyperbola. Very useful in navigation and so on. All of those GPS devices you have. Okay, y equal to 1 over x. What is at issue here? I have chosen some point A. So some point has been called A. We have gone up here. We have figured out what is the tangent line going to be. Well, we really had just found out what is the slope of that tangent line going to be. We learned that the slope of this line is equal to minus 1 over a squared. What does that mean? If you had chosen a to be 2, that slope turns out to be minus a quarter. If you have chosen a point to be 10, slope is going to be minus 1 over 100, and so on. Notice that the slope is negative here. If you choose a to be whatever number that you can pick, of course you cannot pick 0 because that 0 function is not defined. Anywhere else you pick, square it, so that's positive. A minus 1 over that number is going to be a negative number. Slope on this function everywhere is negative. Now suppose the question was posed like this: find equation of tangent line to y equal to 1 over x at x equals to, say, 3. What does that mean at x equal to 3? That means your a is 3. X coordinate of the point at which the tangent line is being investigated is 3. So I already know what the slope is going to be. Slope, I learned here, slope is minus 1 over a squared. Slope is minus 1 over 9. So a problem like this, I really need to start from the beginning here, go through all of that, come, I have the slope. Now, once I have the slope, I ask myself the following question. Here, x is equal to 3. What is y? Well, of coordinate of y coordinate comes from here. Y is equal to 1/3. So I have the slope, I have the point. Point is 3 1/3. So equation of tangent line is going to read like y minus the y of a given point is equal to the slope times x minus the x of the given point. So that gives us point slope formula for the tangent line. Now, if you have the desire to rearrange this thing, you can multiply through and carry the items to the other side if you wish. So you can write y minus 1/3 is equal to minus 1/9 of x. Minus 1/9 times minus 3 simplifies to 1/3. Now you might want to move this to the other side. Y becomes minus x over 9, a third and another third gives you 2/3. So this is the alternate format of it. This is going to be your y-intercept, and the slope is minus 1/9. So y-intercept of this line comes out at 2/3. Slope comes out as minus 1/9, and so on. So these are characteristics of this line. Let's go ahead and quickly take a look at our next example, exhibiting some of the other tricks we need to know. Example 3. I'm going to talk about y being equal to radical x. Again, our question is find slope of tangent line at A. We know the drill now. Limit of x going to A of f of x minus f of a over x minus a. I forgot to mention that by now we know this is the name of the function f of x. So this is the limit of radical x minus radical a over x minus a as x approaches a. We have seen this kind of limit operations. The way to handle them is to multiply by the conjugate. Let me make room for it and write it here. Limit of radical x minus radical a over x minus a times. So we multiply this thing by an expression that hopefully simplifies things for us. That expression has to be different than 1 because we don't want to change anything. So I multiply that with this. The advantage is that when you multiply the numerators, you can use product of a conjugates. So let me remind you, these are called conjugates. This and this one. So so if you have two terms that are being subtracted, the conjugate of that is when you add them. Big deal about it is that when you multiply the conjugates, you get difference of squares. So if you had square roots go away. That is the issue here. So radical x times radical x, that just becomes x. A's also take care of each other. In denominator, I have the same thing, plus this item, we have to drag it along with us. Still the same limit. You notice that this expression and this expression are the same. We went through all of this just to achieve that. And now I can say this is equal to limit of 1 over radical x plus radical a. As x goes close to a, Now when x is very close to a, so radical x just is close to radical a, and this whole fraction boils down to 1 over 2 radical a. So that is our final answer. The slope is 1 over 2 radical a. One more time, let's go make sure we understand what is it we are talking about here. My function was radical x. Radical x, half of a parabola, looks kind of like y is equal to radical x. So if I have chosen to start at the point A, and my question is what is the slope of tangent line here, slope of tangent line is m is equal to 1 over 2 radical a. So if this a was 9, slope turns out to be 1/6. Is that right? Square root of 9 is 3 times 2 makes it 6. If this was a was 100, slope is going to be 1 over 20, and so on. Maybe I ask you to do the following. For next item we have example 4, f of x. Let me write in a stronger color. F of x is 1 over radical x. So we have a combination of a radical and a fraction in the same problem. You want to find slope at, to do it in general, let's do that. A, if they had given you a particular number, you had two choices: to just work it out with that number all the way through, or do it at this general quantity A, and at the very end go ahead and replace the number you actually want. This is preferred because once you do this, that final formula is good for any kind of point that you have. So again, with one stone you're killing lots of birds. You're handling lots of questions all at the same time. That's an advantage of having a variable. Okay, now could you pause this and go ahead, do this problem, and come back and double check your answer. I get started here. Slope of tangent line is equal to, start, limit of f of x minus f of a over x minus a. X comes close to a. We go replace f of x 1 over radical x, f of a 1 over radical a, x minus a. I cannot emphasize enough that you have to do this thing yourself. So stop listening to me and come back just to check. Limit of x going to a, take common denominator. Common denominator there is radical x times radical a. Numerator is radical a minus radical x. I just cross multiply these two. Common denominator is just a product of these two, which I wrote in that fashion. You could have written radical x times radical a if you wanted to, by the rules of radicals. Let me just remind you, if you have radical x times radical a, both x and a positive, you can just combine it inside same radical if you wish. Moving on, here we have same issue as previous case. we are dividing a fraction by an expression, so I can bring the denominators and multiply them. Radical x a times x minus a. I forgot to write my limit word. One more round. We learned from the previous exercise, standard way to handle these problems is to multiply with conjugate. That's one way. You have other ways of doing it. xa times x minus a. I multiply by, here my conjugate, radical a plus radical x over radical a plus radical x. My x still doing same thing it was doing first time around. Sometimes in these problems, to reduce amount of writing, we might write the slope of a secant line, drop all these limit words all the way until very end where we are all done with all the algebra, then come back, say slope of tangent line is equal to, and take the limit at the very end. This is rather wasteful writing because we are not really intending to take limit at any of these stages. We're just going through algebra. So we might as well postpone that. But when you want to do that, you have to write it carefully, not do mix and match. You start with slope of secant line, drop all the limit words. At the very end, you write slope of tangent line is equal to limit of whatever expression you are handling at that moment. Let's move on here, and I write the answers on next step on the next line. Multiplying the conjugates makes this radical goes away. That is a, that is x. Denominator, I have radical xa, I have x minus a, and now I have one more thing, radical a plus radical x. Okay, the exercise we had with the fractions comes in here as well. This and that simplify, and what do we get? A minus x over x minus a. We just saw that a moment ago. That is going to be just minus 1, our limit again. Okay, we are ready to finish this thing. So when x goes close to a, this x and a become same numbers. Is that right? And under the radical, I'll have a squared. So a squared, if you wish to leave it there, you can take it out. Remember, to begin with, a was positive, so I can write it's minus 1 divided by, this simplifies, maybe I write it the first stage, this is a times a, and here let me also write it out, and then I simplify next step. Well, square root of a squared for positive a's is just a. This is 2 radical a. Civilized way of writing this is to move 2 up front. A radical a. Still other ways of writing this. I can combine this. Minus 1 over 2. What fractional exponent can I use? This a times radical a could be written as a to power of 1 times a to power of 1/2. Net power is a to power of 3/2. So I could have written this as a to power of 3/2. Just not letting go of this problem. Still there is another choice, minus 1/2 of a to power of minus 3/2. So this answer, that one, this one, they are all good. You just have to be comfortable with moving around from one to the other. They are all the same. So let's say this is our final answer for this problem today. Okay, let's go have an example by using the other notation we had for finding the slope. We go back and show you. We had 3 different ways of talking about this. You can write it in this notation, calculate the slope of the secant line like this and take a limit. You can write it with this notation, H notation, or you can write it with this delta X notation. So there are 3 versions of this, and much of the future chapters in the course try to use this one. Slight advantages and disadvantages in either of these things. Let me just show you one example. Find slope of tangent line to f of x is equal to x cubed. Say, let me throw something else also, x squared at x equal to a. So what's our starting definition? Slope of tangent line is limit of, to use the h notation, a plus h. So a is the point that is given, h is the variable, f of a divided by h as h goes to 0. So let's go quickly do this. So I'm taking the limit of, I have to go over here, instead of my x's I want to put a plus h. So maybe I color it so that you see how the substitution goes. Here is our x. Let's go ahead and right hand side write that x in the same way. So I wrap my x's in parentheses. That parenthesis has to be replaced by this one. Okay, that's the idea of substitution. If you want to calculate f of a plus h, all these red items have to be replaced by this purple item here. So we'll have a plus h, maybe I continue writing that color, a plus h. It has to be cubed, and then I need to write it one more time, so let me write it. A plus h, I had to cube it and then square it to do f of a plus h. Then I have to calculate the same thing at a. So I write a cubed plus a squared. That whole thing has to be divided by h, and then h has to go to 0. How do we carry this thing out? Well, you need to know how to square or cube something, and I hope you remember that. Maybe on the side I say, if you want to write a plus, let me write in a different color so it doesn't mix with everything else we are doing here. If you have a plus h squared, well, that one you should surely know. If you forget, just go back and multiply it out. This will be a squared plus 2ah plus h squared. If you want to know a plus h cubed, you really need to memorize this. That's going to be a plus h squared times another a plus h. So a plus h squared, we already know what that is. So I write this as a squared plus 2ah plus h squared, and then times a plus h. Now I should just multiply it out. A squared times a cubed, 2ah times a, 2a squared h, h squared times a. So let's write that as always a is up front, ah squared plus h times a squared 2ah times h squared times h. So we are adding this expression to all of that. What's the net total? Well, I have a cubed 3a squared h 3a h squared and h cubed. So I need to give myself room, so let me go ahead and I write here, I guess. So that expression that I have here is equal to limit of h going to 0, numerator, instead of a plus h cubed, to write all this mess here, a cubed plus 3a squared h, it's 3a h squared plus h cubed plus a squared plus 2ah plus h squared. That is the second piece here. That is going here. Minus a cubed a squared over h, but plenty of cancellations, or maybe not plenty, but some cancellation, a cubed, and then you have a squared. Whatever is left, let's collect it. And factor h out of it. Well, I have a factor of h here, 3a squared, from this one 3ah, from this one h squared, from this one will be 2a, and then I forgot something. I have from this one I have an h. So let's just track them so that we know where they came from. This came from here, this came from here, of course, this one, and this one. Everything else was gone. Now I go here and say limit of h's cancel also. That is the big news. H's went away, and you have 3a squared plus 3ah plus h squared plus 2a plus h. H is going to 0. Now we are almost home. When h goes to 0, these expressions, this tends towards 0. So h is getting small, times any number in front makes it 0. This one goes to 0, this one goes to 0. You are all left with just 3a squared and a 2a. So what's the opposite of this whole calculation? Slope of tangent to y is equal to x cubed plus x squared at a is, here's the slope, m is equal to 3a squared plus 2a. Very first example we did was this simple case of just x squared. You remember slope for that one was 2a. You realize now that the contribution that is coming from x cubed is this 3a squared. In the next chapter we are going to condense all of these things so that this type of a problem will be done in as short of a step as you see, just going from here to there. But right now you are required to go through it in this long fashion way, derive it from scratch, as opposed to using ready-made formulas. Okay, let's go ahead, take a look at the last item we've promised, which is applications to finding velocities and questions that come up in physics. Let's do a quick review. Suppose an object is thrown up in the air, so it's traveling like this, it goes up. We want to track the location of it, so it's good to have an axis. So I might just use the y-axis itself for my axis. So I'll have the y-axis itself and the ball just thrown up in the air, and perhaps hopefully it just comes back down or whatever wants to happen to it. So I will have y. I check to figure out where the particle is or the ball is at any given moment. So y becomes a function of time. So t for us is presenting time. Position in this problem is shown by y. If I want to figure out how fast this one goes, well, I need the notion of speed or velocity. That is displacement. So we have the notion of velocity, that is displacement over the time interval. Well, when you throw a ball at the beginning, it goes very fast. When it reaches its highest point, it slows down and then eventually it turns around. So when you're talking about velocity, if you calculate displacement from one location to some other location, velocity is changing during all that time. So what you get by this definition is the average velocity. What about instantaneous velocity? What do we mean by instantaneous velocity? So the time interval of observation has to be shrunk to a single point almost. Displacement then is also going to become very small, and the ratio at the limit is going to be our instantaneous velocity. So instantaneous velocity is going to be the limit of the displacement divided by the time interval or interval of time so this is really length of the time interval. The limit is taken as the length of the time interval goes to 0. So let me abbreviate that. How should we abbreviate this thing? The length of the time interval goes to 0. So if I want to figure out what is the average velocity, say between t equals some number a and t equals some number b, that is, I have waited 10 say a seconds. At a second perhaps the particle is here, at b seconds the particle is here. Well, I have to figure out the displacement. That is going to be the displacement. Now I have to figure out how long I waited. Well, from a to b I waited b minus a seconds. Divide them and then I get my average velocity. Well, at any given moment, where is the particle? Here's a description. Plug the value for time. output is going to be the location. So at t equal to a, y is f of a. At t equal to b, y is equal to f of b. So your displacement is the difference of these two, is f of b minus f of a. Time interval, time it took for this trip to happen, is just b minus a. So now you have the average velocity on, so average velocity, we have the average velocity calculated on interval from, say, a to b. That is f of b minus f of a divided by b minus a. Does this remind you of anything? Well, that is really just definition of slope of the secant line we had at the very beginning. So average velocity and slope of secant line are the same thing. What if I want to figure out instantaneous velocity? Instantaneous velocity, I have to choose a certain moment at which I want to calculate that. I no longer have an interval. The interval has shrunk to a single point. So I have to let, for example, b come close to a. So instantaneous velocity is going to be the limit of this expression, f of, say, b minus f of a over b minus a, and say in this case b comes close to a. I could have used any letter here for this variable, so long as it doesn't collide with other letters I've used. So I could have used t, b, or anything. It would be all fine. Instantaneous velocity, we better have a letter for that. Well, velocity starts with v, so v. At what moment are we calculating? Everything is geared to this a. Velocity at time a is equal to that. Whenever we say velocity, by that we understand instantaneous velocity. So many cases you see this word has dropped. If we want to say average velocity, we have to say it. Average velocity, you have to say the word average. If you don't say anything, we understand you're talking about velocity. Okay, let's just go ahead and do a quick practice on this issue. Suppose we take that example that you're going to see very often in this course, in your physics classes, in your engineering classes. The topic of a projectile. You throw something up in the air, it goes up there and comes back down. That's the simplest thing anybody could wonder about. How does that motion happen? So suppose I have the vertical location of a ball or something given by a function called f of t, and it's given to me as minus, say, 16t squared plus say 64t. So I say the location of a, say a ball is given by this. Well, where do such formulas come from? Well, in your physics classes they are going to tell you a lot more about it than we are going to say here, but it's a very standard one. What we are interested in right now is a find speed at, say, at t, anytime t. Find the speed of the ball at time t equal to 1. So here's a question 1, question 2, question 3. Next question, when does it reach the highest point? So it's a standard question. When does it reach highest point? And 4 is another standard question. When does it hit the ground? One more question we might ask, with what speed does it hit the ground? Okay, how do you find speed? Well, we learned the word speed is a bit different from velocity. Maybe I should have just used the correct definition. Find velocity. Same thing here. Technically speaking, speed is a positive number. So speed is the layman's impression of velocity. You have to take a velocity, take an absolute value of it, and that's going to give you speed. So let me just mention here on the side, technically in our courses, speed is absolute value of velocity. So sign and directions all stripped off, and then you get the okay, let's come back to this problem. We wanted to find the velocity of a ball that is moved according to this formula. So how do I get the velocity? I say velocity is equal to the limit of, let's use our h notation here. Let's f of t plus h minus f of t divided by h as h goes to 0. So what's the meaning here? T is time, f of t is location, h is how long I wait from start of the observation. So at the end, time is t plus h. This is location at the end. Location at the end minus location at the start is the displacement. Displacement over time is the average speed. Let the time pass to go to 0, the average becomes instantaneous. So how do we carry this out? I have to go ahead and, just like the previous problem, instead of t here and this t here, I have to put this t plus let me write it a different color, say here t plus h. That red has to be substituted by this blue stuff. So I'll have a limit of minus 16 times t plus h squared plus 64t minus this is this minus the f of t, just copy of what we have, minus 16t squared plus 64t. The whole thing divided by h as h goes to 0. Here we have limit of h going to 0. I open the numerator, minus 16 t squared minus 32th minus 16h squared. I made a mistake here. It was supposed 64 times t. Let me erase this thing and write it better. I was supposed to do a complete substitution, t plus h, and then minus this. It became a bit messy over there, sorry for that. Let's continue. Plus 64t plus 64h minus makes it plus 16t squared minus 64t. All of this divided by h. Well, fortunately, simple cancellation take care of quite a few of these. 16t squared, 16t squared, 64t, 64t. Whatever else is left gives you a factor of h. So I'll have limit of h, no, minus 32t minus 16h plus 64 divided by h. H goes to 0. Now these h's cancel. This is equal to limit of minus 32t minus 16h plus 64. Still h goes to 0. When h goes to 0, 16 times h also goes to 0. We are just left with minus 32t plus 64. Here's the final answer. Let's rephrase. If location is, how did we write it? This is our location. Let's not copy that. Location is y is equal to f of t is equal to minus 16t squared plus 64t. Then velocity, you remember velocity means instantaneous. Velocity as a function of time is this minus 32t plus 64. So that's the conclusion of part 1. What was other question? What is the velocity of the ball at time t equal to 1? No time to harvest all of our informations and quickly answer everything. At t equal to 1, velocity is, t is just 1. Velocity at time 1 is minus 32 times 1 plus 64. Well, simplify that to 32. Part 3. When does it reach the highest point? So, what is the characteristic of highest point? When a ball starts, goes quickly, and slows down, and then turns around and comes down. What happens at this point? Momentarily it stops in mid-air. Up there, speed becomes 0. So at turning point, velocity is 0. Okay, that is a crucial fact. We always use this when you want to figure out the high lows of the strips. At those points, the velocity becomes 0. So we go indirectly. Take the velocity. Here's the velocity. At any time, t is minus 32t plus 64. Velocity is supposed to become 0. Well, you solve that. What do you get? T becomes 64 over 32. T becomes 2 seconds. It takes 2 seconds for this ball to reach the highest point. Okay. So we make a note of this. Question was, when does it reach the highest point? If I had asked what is the highest point, to figure out the highest point, that's not asked there, but the highest point. So the highest point of trajectory, how do I find that out? Well, remember, f is given for us. This is the position. location is this. If you know the object has reached its highest position at time equal to 2, so I'll go ahead and put t equal to 2 here. So I get, I had f of t is minus 16t squared plus 64t. So f of 2, this 2, because of this 2, f of 2 is equal to minus 16, 2 squared plus 64 times 2. So you have minus 16 times 4, that's minus 64 plus 128 makes a net of 64. This is the highest point of the trip. Next question we were asked was, when does it hit the ground? Okay, that's just like this. We had a characteristic for the turning point, velocity becomes 0. What is the answer to the other question? How do I figure out when the object hits the ground? Sometimes the students make a mistake of thinking that when it hits the ground, the velocity becomes 0. Of course, after it has splashed on the ground, it stops. Well, you can say its velocity is 0, but that's irrelevant. Just before it hits ground, that is what we are looking at. So what is the ground? Ground is just the origin of our coordinate system. So I go ahead, set y equal to 0. Item 3, ground typically means y is equal to 0. So that's another fact to keep in mind. Typically your coordinate system, you have a ground here, your coordinate system built on top of that, and ground itself is 0 unless you move it somewhere else. Well, here is our y. Y is equal to f of t is equal to minus 16t squared plus 64t. I set it equal to 0. How do I solve this? Well, easiest thing is to factor minus 16 t minus 4 equal to 0. Either of these factors can be equal to 0, so either minus 16t is 0 or t minus 4 is equal to 0. This tells you t equal to 0. This tells you t equal to 4. Which one is met? Obviously t equal to 4. Or what is this doing? This is when you just took off. You started here, you went all the way up, turned around, came down. So this was t equal to 0. When you struck, t was equal to 4. So at time t equal to 4, it strikes the ground, and here's the answer to part 4. Part 5, what's the velocity when it hits the ground? So remember, here's our velocity at any time. How fast is it going when it's just hitting the ground? Remember, just when it is hitting, not after it smashed the ground. So we say velocity turn out to be minus 32t plus 64. So 4 seconds after launch, how fast is it going? Minus 32 times 4 plus 64 is minus 128 plus 42 makes minus 64, excuse me. Just keep in mind that this 4 is this 4 here. This is the time to strike. At the time of strike, that became the speed. So if you want to give units to these things, it was all feet and seconds. So this will be 64 feet highest it goes, and 64 feet per second, how fast it's going to go when it's hitting the ground, and so on and so forth. Okay, so we covered items that we have been talking about since the beginning of the semester. We quickly went over everything. This section and next section are essentially recapping everything and cleaning up before we move on to the next chapter. Make sure you increase your speed and learn how to find the slope in a variety of cases. In the next chapter, we are going to introduce shortcuts to all of these things so that we can do a lot more in a given amount of time.